If you haven't seen structs before, they're sort of like Java classes, only they don't have any methods. No methods are allowed in C structs. A struct is just a way to put unrelated data types into a single object, just like in the case of, well, not just like, but just like, sort of like in the case of classes, where you can have a class, let's say person, a whole bunch of data members. Same idea with structs, only the difference is that there are no methods, no functions, no member functions in structs. Those of you who've had C++, you know that structs in C++ can take member functions, but in C, those are not allowed. Okay, it's a little bit more primitive. So arrays are ways of putting data types that are the same. So an array of ints can only contain ints, no doubles, whereas a struct can be used to have, for example, an int and a double, or an array of characters. So a struct can have arrays, and then we can also create arrays of structs as well. Okay, so in this particular case, in this particular example, we're saying this statement says that we have a struct called person, which has 3 data members. One's an int, the second thing is an array of 30 characters, and then the third thing is an array of 100 characters, up to 100 characters. And when we actually instantiate that struct, we can say, and this is another difference, we can't just say person, we have to say struct, and then the name of the struct, in this case person, and then finally the name of the variable. So this is a little bit different from C++, where you could omit this struct command. So in Java, we don't say class person X, we just say person X, but in C, we have to use struct. That's just how C works. And we can also set up pointers, but for now, let's just omit that. Let's not worry about that. So in this particular case, we set up this variable called guy, which is of type struct person. We initialize the int ID to 2349, and we initialize this array of 30 characters to this string, and we can do that. So remember, this will be null terminated, and then the second array of 100 characters is initialized to this string. Once again, has a null termination character at the end. Okay, so since structs are programmer-defined types, the convention is almost always to use a type def. So what does this mean? So this means that whenever you see a struct, chances are you will see a type def, and then all of the things that deal with how to set up the struct, and then finally we see this, which is an alias for the struct person and all of this. So now, with using this type def, you no longer need to say struct person guy. You can just say, you can use the alias, that is this type def value. And so now this is equivalent to what we had before, where we said struct person guy. Now we can just say whatever this thing at the end of type def was, person type guy is equal to exactly the same thing. Okay, so this is just convenience. We don't have to use this. We can use this all the time. It's just saves us. If you use a type def, it saves us from always saying struct something. But that's not. Some people like it, some people don't. It's up to you. Okay, so the fields of a struct are accessed as in a class data member. By default, all struct variables are public. So this is unlike classes, where we can, in Java, we can say what the visibility of each data member is. We cannot do that in C-style structs. They are all public. So if you set up, for example, a variable of this type, you can set all the variables, set all the data members using open close curly braces. And we can, for example, access these data variables using the dot notation, which we have in Java too. And since guy is not a pointer but an actual instance of this struct, you just use the dot operator just like we did in Java. or statically allocated objects in C++. Same thing. And we can print them. So for example, remember that ID is an int, so we use printf or fprintf with a %d. We can print out a character of an array of characters using the %s for null terminated strings, and same thing for the next data member address. Okay. So it's common to have pointers to structs. So for example, we set up guide to be, in the previous examples, we set up it to be a statically allocated instance of this struct, and that's going to be allocated on the stack. We can, for example, have a pointer type. So we can say, we can type def this struct person as person type, and then we can say, all right, now I need another alias for pointers to this type of struct. So this type def is saying I'm going to create a new alias called person pointer, and this is going to be equivalent to a pointer to this person type, which is actually just an alias for a struct. Okay, I hope you can track all of that. So now we can say guy is going to be a pointer, and we can use malloc to allocate dynamically from the heap. Remember that whatever malloc returns, you have to typecast into whatever type you have on the left hand side. So this is person pointer, so we cast it as person pointer, and everything is fine. Now we have to use the pointer notation. We no longer say guy.id, we have to say guy minus greater or arrow, which is what it's usually referred to as, guy arrow id. Initialize it to something, and we can copy guy arrow. We can copy to guy arrow name the string, which will copy the null termination character to, and then same thing with the address. Okay, so take a look at this. Look at the differences between using statically allocated objects like this, which is allocated on the stack, versus dynamically allocated using malloc on the heap. When you do this, when you have pointers, remember that you have to use the arrow notation minus greater or arrow, and then instead of the dot operator for accessing the different data members of this struct. So for example, here it is, when we print it out, when we read from that data member, we have to say guy arrow id. When we try to access the string name, say guy arrow name, and so on. Now one more thing that we won't quite get to in this chapter, but we will need pretty soon in the very next chapter, is unions. Unions are like structs, but it's a way to put unrelated data types together into the same memory. So this looks a lot like structs. We've replaced the word, let's say, struct by union, and then what we have is things of different type. But here's the very key difference. This is very important. This int or double union can only have one of these things. It can only have one int or one double. These can be different sizes, but the size of this union will be the size of the largest quote-unquote data members. So these are not data members. These are actually occupying the same area of memory. And it's up to the programmer to figure out what is stored. Is this union storing an int or a double? You don't actually know. There's no way to really check exactly what it's storing. You just have to keep track yourself. So how do you use this? So you say, just like with structs, you say union, name of the union, and the name of the variable. You can store an int at any time, and you can switch it to storing a double by accessing the double quote-unquote data member. When you do this, you actually overwrite the last thing that you wrote. So first time around, you say that the int is going to have the value 10. You use 4 bytes because that's how big ints are. And then after that, if you use the the double data member, you're going to use 8 bytes because that's how big doubles are, and you're overwriting this, we're overwriting all of this union, which means you overwrite whatever, if you had a 10 in there, you write over the 10. So why would people want to use this? Because it's confusing. You don't know if it's storing an int or a double in this case. Well, the reason is to save memory, and that's critically important in a lot of operating system code. And so that's where this is used. When you do some low-level programming, it's often convenient to have a union so that you save memory. You can store either an int or a double, but not both. And the reason is because you can have more than 2 data members. You can have 3 or 4, however many, but the thing is they all use the same memory, and so you better keep track of what you stored in there last, because that's what's going to be in there. Okay, that said, we're not going to really deal with unions so much right now. We will in later chapters. Okay, now let's take a look at information about a file. So let me just back up and mention a few things that might be obvious, but maybe I just want to emphasize this. So when you have a structure like this, keep in mind that actually all of the files are in data blocks. Directories are actually just a tiny block which contains the names of the files and the inode numbers. So if you have a directory, it would look something like this. Something like this chunk of memory. But what that chunk of memory would contain is the inode entry for each file and the name of the file itself. So a directory would actually also have an inode entry which will take you, so let's say the directory /temp, or let's say /user/bin, for example. /user/bin will have an inode entry which will take you to some area of memory. So now all files and all directories are actually flat. There is no hierarchy in the actual data blocks themselves. A directory is just actually just a simple file, and in that file for a directory it will have an inode number and a file name for each entry in that directory, and the inode entry will take you back over to here, and then somewhere in here is the inode entry for, let's say, the ls commands, which is in /bin, and that in that inode entry will be the actual address for the ls command program itself. The contents of the file will be in data blocks. So each file has some number of data blocks. They're all stored as data blocks. It's pretty flat structure, but the hierarchical structure of directories comes about in the way they're stored. Okay, so the way they're stored in the actual directory entries, and we'll get into some of the details of this. But keep in mind that this is really a flat structure. The hierarchical structure is all completely independent of these inodes. Okay, you will have a chunk of memory, a data block, that tells you what all the different files are in a directory, and then that just gives you sort of a pointer back into this inode table.